Alright, in this section I want to show you how to implement PCA in Python and integrate that into the classifier data flow. For that purpose, I'm going to show you a pretty interesting example in face recognition, because in this particular case it's relatively easy to implement and you can visually see the principal components and the way that it works with a classifier. So facial recognition is something we're all pretty familiar with now. For example, it's used to unlock your mobile phone, and it's used in all sorts of security and surveillance problems. Now, one of the challenges with facial recognition is that the images can be somewhat high dimensional. Even in the pretty low resolution black and white images that I'm going to show you here, there's almost about 2,000 pixels per image, which means that a classifier that's going to work on the raw data would have to have a pretty large number of parameters. Now, PCA is kind of a natural idea to use when looking at a data set like this, because you would think that the facial images have a relatively small number of degrees of freedom. I'm going to illustrate that actually graphically later on. And what that means is that we should be able to transform that image to a lower dimensional representation prior to building a classifier. For this demo, I'm just going to illustrate this on a very, very simple data set, much simpler than you would see in any commercial system today, just because it's easy to work with and we can do it very quickly. This data set was generated almost about 20 years ago from faces of celebrities and politicians that were taken from the web. And at that time, it was considered a pretty big data set of about 13,000 images. Again, it's nothing close to what would be used in a commercial system today, but it's enough to just illustrate the basic concepts. All right, with that introduction, let's dive into the Python code on the Colab website. Okay, so as usual, I've placed the demo on the GitHub site. Remember, the links for the GitHub site and all the material are in the links of this YouTube video below. So you can, as usual, clone the entire GitHub site to your local machine and run this demo there. But I'm here going to run it on the cloud in the colab.research.google.com page. So if you want to do it here, just go over to this website, select File, and then Open. You're going to get this dialog box. Select GitHub as usual. Put in my name, https://sdrangan. Select the repository for this class, intro.ml, and scroll all the way down to unit 11. And this is the first demo here on EigenFaces. So that should open up pretty quickly. The first command just imports some standard packages. As usual, it asks our permission. First command takes sometimes a little bit of time. The next command is what's going to download the data set. So I'm going to launch that command because it takes a little bit of time. So as I mentioned, the data set is from this labeled faces in the wild, and that is used so widely in machine learning classes and other demos that the sklearn package has that data set built in. So you can just get it with this command fetch lfw people, and in this class case I'm going to make sure I get classes only with about at least 70 images, and then it downloads it into this data structure. Actually, in this case, it ran immediately because I had the virtual machine already open. The first time you actually run this, it might take about a minute or so, download about 200 megabytes of data. Okay, let's take a look at the dimensions of this data. we can see from looking at the images field in it that they're 50 by 37 images each. So they're pretty low resolution, but enough, we'll see, to get a reasonable classification accuracy. And if the data is stored in this matrix X, and that has 1288 rows, one for each sample. Now, in this particular case, there are about 7 classes, and the numerical index for the class is this vector y, and each class would correspond to one person. And I'm going to show you the people in a second. So we have, if you divide the number of faces, actually let's go ahead and do that. So if we divide the number of samples with the number of classes, we get, there's about 184 face images or samples per class on average. So there's many fewer classes than there are pixels per image, so we're going to have to do some type of data reduction. All right, let's just first plot what these faces are and who they are. So I've just created a simple program to do plotting. Remember, the command for that is imshow, for a black and white image at least anyway. I'm going to randomly select maybe 4 of these images and plot them. All right, in this case, you see the kinds of people in this data set. If you're not familiar with them, these are all American politicians or political people. About 20 years ago at least, Colin Powell, George Bush, who was a former secretary. This particular case, I got him 3 times. Let's do another random set. In this case, I got Tony Blair here, another British politician in this case. All right, and there's about 7 of these people. And the problem is, if I give you an image, can you recognize which one of the 7 people it is? So the first thing I want to do is try to show you how to do PCA manually. Manually meaning just doing it using the singular value transform. So we talked about the mathematics of that in an earlier section. Let's just do it in Python. It's fairly straightforward. The first thing we want to do is subtract the mean from all the columns of the data. So I'm just going to compute the mean here and subtract it and store it into this XS. And then we take this economy SVD with our numpy's built-in SVD command. Now remember to set full matrices equal to false, because we don't need all those extra 0 columns. Now if you recall, the eigenvalues of the covariance matrix are just the singular value squared. So I'm just going to get them by squaring those singular values. And I want to plot the portion of variance, which is the cumulative sum of those eigenvalues divided by the total. So when we plot this, we get this graph here. And the way you read it is this. So this on the x-axis tells you the number of principal components that you could use. And as a function of that, this is how much fraction of the variance we would capture. So we see here that after about 400 principal components, you're pretty much capturing the total variation in the data. So even though the data actually has about 1800 pixels in it, most of the variation, almost all of it, is explained in 400. So we've already gotten some amount of data reduction by going to 400, and maybe, depending on how the classifier works out, we could get away with, say, 95%, which would be about 200, or maybe even lower. Okay, we can also get the principal value decomposition, or the coefficients. And remember that the principal value decomposition says that I'm going to write each x as the mean plus some coefficients z times the principal component vectors. And you can get those coefficients just directly from the SVD by looking at the left part of the SVD multiplied by the singular values. So if I wanted to get the 20 components, I would just use this syntax here. So that is the manual way to do it, but most common, it's more common at least, to use it sklearn's built-in methods for PCA, and you can do that pretty easily as follows. So first of all, the PCA object is in sklearn's subpackage called decomposition, and then you create a PCA object and tell it the number of components you want to use. So then in this case we'll use 20, and then there are some other options which really just apply to the scaling. And then what you do is you take your data and then you would fit that PCA on this data, in which ways it will learn what the PCA components are. So let's go ahead and do that. It's very fast, it does it. And in this case here, we can look at the coefficients that we would have got from, from the SVD, or we can look at what they would have happened from the PCA, and if you plot out the first few values, you see that they are the same, excepting there's some sign differences, but that's really immaterial. This is slightly different here because this is this whiten value, and with the whitening values, it doesn't include the multiplication by the singular values in the coefficients, but it applies it later. We can also look at the PCA coefficients, and those are in the PCA components like this, and we can print them out, and they also match what we would have gotten from the SVD. So feel free to use either. I'd probably suggest that you use the PCA in sklearn because it's a very efficient implementation, and it's you don't have to manually deal with the SVD, but you will get the same results if you use the SVD. All right, now that we have computed the principal components, let's look at how good of an approximation they are. And for this purpose, what I'm going to do, I've written the code here to do either using the PCA, that's sklearn's reconstruction, or the SVD. So if we use PCA, I'm going to fit that PCA object and then get the coefficients along that with this PCA transform. And then what I'm going to do is for each image, what this code does is going to reconstruct a version of that image using a limited number of PCA coefficients. So for example, what I do here is I take the coefficients and I get some smaller set of them, and then I take the inverse transform, which gets back the values. So let's do that here. And this is kind of what we see. So these are two images. One is Colin Powell on the bottom, and the other is George W. Bush. And the full original image looked like this. If we use no principal components, we're just using the average value across the whole data set. And that looks like this kind of scary, ghoulish mask, but that just happens to be the average in this case. And so it's already actually recognizable as a face. It's just not clear which face it is. And as we add principal components back into the reconstruction, we get something that's more and more accurate and close to the original face. So we start to see some features here which are getting close to Colin Powell, and it gets more and more accurate. Although you see here that even at 100 principal components, it's not obvious who this person is in this case. So there's still a lot of smaller details that need to happen in a few more principal components. All right, let's actually plot the principal components themselves. The principal components themselves are actually images, or they're the same dimension as the input space, so they can be also represented as images. So if I plot them here, you can see that each principal component kind of captures some degree of freedom across the data. So for example, this one probably just is kind of overall brightening of the image. This one is some kind of overall brightening on one side. This is on one corner, maybe to capture the shape of the face and so on. So, and this one here maybe is capturing the strength of the eyebrows above that. So these are the dimensions in which the image could change. And if we take, say, hundreds or 200 of these, take a linear combination of them, we can hopefully reconstruct, or at least approximately reconstruct, the face. So now we have done PCA and looked a little bit visually of that on the data. Let's show how to use this for classification. So for this purpose, I'm just going to try to build a simple SVM classifier on top of the PCA. So let's start to illustrate this by doing a train test data split. So I split the data into training and test with sklearn standard method. I'll use about 25% for training. You could actually do k-fold validation. I'll just make this very simple here. Now, in this case, you really have two parameters that you can select from. The first is, I'm going to, as a first stage, take the original image and project it down to a lower dimensional space. The question is, how low dimensional should I use? If I use very low dimensions, I have less parameters in my classifier, so there will be less variance error, but I'm throwing away information, so there will be higher bias error. The second is, within the SVM itself, there's that parameter gamma for the radial basis function, if you recall, and that also has a bias variance trade-off. So what we would want to do is search over both of these to find out the best value. And that we are going to do with cross-validation. So for every pair of values here, I'm going to train the classifier and then measure the accuracy on the test data. Now the SVM actually has a third parameter, C, if you recall. Just for simplicity, I'm going to keep that as 1, but feel free to play around with that as well. So whenever we set up a cross-validation like this, we look at the values I can test for both parameters. I'll try about 5 different values for the number of principal components. One is a very low dimensional representation of 25, go all the way up to about 200 principal components. And similarly, I'll search kind of logarithmically over the gamma values, and I'll just fix that C value in this case. Oh, in this case, I selected it to 100. And then I have a double loop where I loop over the principal components, and then I loop internally over the gamma. So for each principal or number of principal components, I create a principal component object, I fit it on the training data, and then transform the training and the test data. So the transformed data is really just the coefficients of the data in the PCA vectors. And then I run the classifier on the transformed data. So I create a classifier with the appropriate gamma, and then I fit it on the transformed training data, and then I can make predictions on the test data and measure the test accuracy. And then if it's greater than the best one, I keep the maximum. So let's go ahead and run that. This is not too slow. It takes a little bit of time. And you can see here that it's looping over all the principal components and all the gamma values. And we get different accuracies through this. The maximum maybe being around 84% here. Just so you can visualize this, just create a little simple plot. You get different values, a little bit different values, because there's some randomization in the scrambling and things like this every time you run this. But you can see here that the maximum value in this case, if I look over both the gamma values and the number of principal components, the maximum value is about number of principal components is 75. So even though the data was 1800 pixels, it actually was best to transform it down into a fairly significantly lower dimensional space, a dimension of about 75, which is it's just about 5% of the original data. And after you do that, you can get an accuracy that's on the ballpark of about 80-85% or so. On the other hand, if you pick much larger numbers of principal components, you can see that the accuracy starts degrading very, very quickly. So you definitely are getting a big benefit from using this PCA transformation. Let's just plot or look at the refit with the best classifier. So I'm just going to get the optimal number of principal components, the optimal gamma, and redo those steps. Indeed, as I said, you get an accuracy of about 84%. Let me just wrap up a couple of things. Let's take a look at the confusion matrix and some other stats. The confusion matrix in this case tells you for each class where the errors were. So for example, here in this class, the fourth class is George W. Bush. So you can see which other people he was getting confused with, and I think perhaps Donald Rumsfeld here in this third, for example. And so we could take a look at it and go through these numbers, but actually it may be more illustrative to look at some pictures of cases where the classifier was correct and then some cases where the classifier was wrong. So let's look at the correct cases. So in this case, the true image is Tony Blair. So that was the original image. But after that compression, this is what it was looking at. So remember, we did this transformation and it was able to guess in this case that this person from this compressed image was Tony Blair. And in this case is Gerhard Schröder, who's a German politician, and it was doing the guess from this compressed image. So you can see that the compression does lose a lot of details. If you were trying to create a news photo, for example, this is a pretty bad approximation. It's a pretty blurry version. You would prefer to look at this. But from the perspective of an SVM classifier looking at trying to guess the face, this was actually preferred because the classifier had less degrees of freedom to work with. All right, let's take a look at what happens in some wrong cases. If I do this, this was Donald Rumsfeld, but by the time it got compressed, you see here that the classifier thought it's George W. Bush. And similarly here, the German politician also got classified so badly, approximated, thought it too was George W. Bush. Now, I'll be honest, I'm not super familiar enough with these faces. I don't know who I would have guessed these two people are from these approximate versions, but clearly you can see that they are noisy and that, or not noisy, but blurred, and for that reason the classifier makes some mistakes. Okay, so that wraps up this quick demo of using PCA through SVD, also through Python's built-in tools, and how to integrate that into a classifier. I'm hoping that that will expand the set of problems you can look at next time you have a problem which has a very high dimensional data and you don't have very many data samples to work with, or you just want to build a simpler classifier. Think about using PCA as an initial step to make that simpler and give it a shot with what you have learned today.